Now, what I ought to bust out is the chemistry GRE test. Y'all be mad at Miss Poe for that. Actually, y'all should take. Actually, what I should do is I should just give y'all the AP chemistry test for your final and call it a day. No? Okay. So, last, what do I do in a titration that I need you guys to be aware of? So, I'm going to look at the example that we were working yesterday of a weak acid strong base. So, I think that was number 5, right? So, we were looking at number 5, which was acetic acid titrated with sodium hydroxide. And we went through initial pH at pre-equivalence point, which is in like the buffer region, all right? And then we went through what to do when you're at the equivalence point for a weak acid strong base titration. And that's the hard one. Rather, that's the one that has a whole lot of parts to it. Yes. And that is the one that I hope, so in lab today, when we go down there and y'all are cleaning up some, I mean, we're going to just use this lab time today to study, okay? And y'all work on your worksheet, or I can come up with other practice stuff for y'all to, you know, like I said, but we can definitely work another what to do at the equivalence point example for sure, okay? But where we are now, I'm going to talk about is on 5, part D. What is the pH when you have added more than the equivalent volume? Okay. So we're talking about the same reaction that we were working yesterday, and we're going to look at just part D. When you've added more than the equivalence volume, okay. I think for this problem, what did we determine the equivalence volume was? It was 25 milliliters, right? Okay, so we determined at the post equivalence point. Interesting. I guess I realized I did that. It is. That's fun. We determined that the equivalence volume was 25. Okay. So anything above 25 is therefore after the equivalence point, right? If you're thinking about our titration curve, right, then we're, you know, anywhere in this region, yeah, post equivalence point, because there's the equivalence point. So we're anywhere in this area, right? In this acid-base reaction that we're doing, so remember, you can always just write the HA, that's our weak acid, and we're reacting it with strong base. And we make the conjugate base, and we make water. Post-equivalence point, you should start off with calculating, well, how many millimoles or moles of weak acid do you have to start? How many were in your beaker to start? How do we calculate how many millimoles of, or how many moles of anything that we have? Volume times molarity. So we had $25 milliliters of acetic acid, and it's 0.1 molar. So that is 2.50 millimoles, right? Okay. How much A minus do we have before the reaction happens? Essentially nothing, essentially 0 before. How much OH minus are we adding in this description? 37.5 milliliters times the molarity of the strong base we're adding, which is also 0.1. So I am adding 3.75 millimoles of base. Right? What do I end up with after? .5 reacts with 3.75. That's what we're saying. Which one of these is in excess now? The base. You have excess hydroxide. How much does that mean of this acid is still remaining? You have no HA remaining. It all got used up. You have how much OH minus remaining? Do the subtraction, right? Right? How much A minus do we have after the reaction? How much gets made? What is the maximum amount of A minus that can get made from this reaction? Excellent. The 2.5 strong acid, 2.5 weak acid that I had all gets reacted to make A minus. Okay. But here's something now to think about. Post-equivalence point. Post-equivalence point. You have these two ions in your beaker. They're both there, agreed? But guys, which one of these ions is a weak base and which one of these ions is a strong base? Which one of these is a weak base? A minus is a weak base, isn't it? What is OH minus? Strong base. So guess which ion is determining the pH at this point. I only care what the concentration of the OH minus is, post-equivalence point. We can ignore any contribution A minus might make to the pH at this point. At what point? Post-equivalence point. We can ignore it. I don't care about it. Don't care. I care about the hydroxide. So I have 1.25 millimoles of hydroxide. What can I do with OH minus? I can find POH. But can I plug millimoles into the POH formula? What's the only thing I can plug into a pH or POH formula? Molarity. So this post-equivalence problem is going to require you to find the new total volume, which is what for this problem? Yeah, what are the two amounts that I added together in this description? Yeah, I had 25 mils of weak acid to start, and I added 37.5 mils. So new total volume, 62.5. Okay. I was worried for a minute that I couldn't do that math in my head anymore. So then what? What is my molarity of OH minus? millimoles divided by milliliters. I got a molarity of 0.0200. So I've got 3 sig figs, yes? Okay. Now find the POH and then answer the question finally with what's that pH. Okay. So again, 3 sig figs in my concentration means my POH value goes how many places past the decimal? 3 places past the decimal. 1.699 is what I got. So then that means my pH is 14 minus 1.699, and I get 12.301 is the pH of this mixture at this point. Okay. Yes. Yep. For weak acid, strong base, pre-equivalence point, this whole little region right here is the buffer zone. And you can use that HH equation. But post-equivalence point, because we have excess strong acid, excess strong base, it's not a buffer anymore. Okay. Pre-equivalence point, while we're adding OH minus, it's not enough. It's just enough to create that buffer situation. Okay. But post-equivalence point, it's too much. So, all right. Absolutely, you may take a picture. Let me move my camera a little bit. Okay, go right ahead. So, guys, I told y'all that, of course, you can look through my solutions worked out for some of these other questions from part 3. And this may be one of the ones that I think we should do, maybe practice with together down in lab. I think maybe number 8, which is one of those equivalence points ones. But the answer is in the slide if you wanted to just check. And then, of course, most of y'all took pictures of this yesterday. So, but okay, so that is the end of chapter 14. Thank goodness. Remember, tomorrow is your test over chapter 14. I'm sorry, I hate that. I hate that. But, and I'm going to let you guys have how many note cards? 2. And I think all of my note cards are down in the lab. So when we go down there, be sure we grab note cards today. Okay. What is available? What do you need to be finishing in active chem? There's the second homework set. And then there's a quiz that I opened up yesterday. Has anybody taken the quiz yet? I haven't looked to see. I didn't think you would, but it's 9 questions. Only one of them, I think, is a multi-step. Okay. Well, maybe there's, well, is that true? Maybe I'm thinking, maybe there's 2 there. Anyways, whatever. There's 9 questions. And I gave you guys 100 minutes. It's an hour and 40 minutes to take this quiz. Okay. Plenty of time. Tomorrow, like we discussed, we are going to just do the tests the whole class period. So I'm not going to lecture new stuff before. Okay. Come at 11:30, start the test. You have the full 3 hours. Please, God, don't y'all take the full 3 hours to do this test tomorrow. Please, Lord, don't do this. Don't do that. Don't do that. Don't do that. But I likely will have something for you to maybe watch, a video of mine to watch tomorrow afternoon, probably. Okay. Let's see how far we get with chapter 16 today. So. Oh, but I changed my mind because I put that because we just went over it. So that could be on the exam. It's fair game now, is what I'm saying. Could be. Sorry. The test is mostly ready. The test is mostly ready. I'm still tweaking and I'm still trying to decide how many bonus questions y'all deserve. Yeah, right. What's the pH of a strong acid, strong base? What's the pH of a strong acid, strong base at the equivalence point? You have to say dead ass 7 to get the points. Okay? You have to write dead ass 7 to get the points. Yes, yeah. When which one is right? It's dead ass 7. I don't know. We were talking. Catherine and I were talking earlier. I can think of one bonus question that you guys might definitely see on there. What is my favorite acid? Acetic acid. Yes. Okay. That's good. That's good. Yeah. What's it? Yeah, I'm gonna ask you to write that formula. Okay. Let's start chapter 16. Does everybody have the stuff? Okay. This is called thermodynamics. It's one of my favorite topics in science. I love thermodynamics. So in Gen Chem 1, you should have covered thermochemistry. Thermochemistry is looking at specifically chemical reactions and how heat moves between objects. That was about heat. We're still going to look at some heat enthalpy related stuff in this chapter as well. I have a little list here of a few things that you should maybe recall from that first topic in the first time we talked about this in Gen Chem 1. Probably the main one I really want us to remember is what is the first law of thermodynamics? Energy can't be created or destroyed. It gets moved around, right? Okay. It's helpful. It's going to be helpful to remember that enthalpy quantity, delta H, is equal to Q. What is Q? Heat. Do we know ways to calculate heat? MCAT, the moles times delta H equation. Okay, so we know ways to calculate that. That's good. Do you guys recall this? You can use standard enthalpies of formation to solve for the delta H of a reaction. We're going to do something similar to this, but with a different property than enthalpy. So we'll get a review. That's fine. And then definitely need to remember that if your delta H is a negative value, or your Q is a negative value, that means your reaction is what? Exothermic. And if it's positive, that means it's endothermic. Okay. Well, let's get started. We got to talk about this word, spontaneity. Spontaneity. So these are the lecture 14. So we're starting a new chapter, new set of lecture slides. 16.1. Spontaneity, lecture 14 slides. When I say something is spontaneous, just in general, what do you guys think that means? Instant, it just does it, just happens. It just happens. Spontaneous means a process that just happens naturally. We can describe a reaction or a process as spontaneous if it happens on its own without what we would call outside input of energy. Okay, so a process that happens naturally. Although, Joe, you said instant, and we're going to see that if you are using the word instant in terms of like time, that's not what spontaneous is. But if it means it just happens, then yes. Okay. Spontaneous, process that happens naturally. I guess the way I'll say it, with no agency from us, the observers. Okay, we don't do anything to make it happen. What's in us? Here's the real simple example of something that is spontaneous. A ball rolling down a hill. That just happens spontaneously, doesn't it? But what about the reverse process? What about a ball going up a hill? That needs some work by one of us. So if you have a spontaneous forward process, what do we know about the reverse process? It would have to be, the reverse process would have to be non-spontaneous. Okay, non-spontaneous. We might need an abbreviation for spontaneous, guys. What should we write instead? Spawn. Okay, spawn. Non-spawn. Let's say that. Non-spawn. I like it. I like it. Okay. Happens naturally means it can be condition dependent. It can be condition dependent. My head's not really with it today, so I'm sorry if I'm kind of blah. So sometimes you'll need to really, pay attention to the description and the problem. Okay, let's say what I was mentioning a minute ago. Spontaneous does not have to mean does not necessarily mean instantaneous. Doesn't mean fast. I want you guys to think maybe about, let me show you an example. Half-lives, right? Decay. If we get to talk about a little bit of nuclear chemistry at the end of the semester, then we'll look at this. But there's many elements that radioactively decay, okay? That means they split in some way, they give off some particles, okay? And they're changing. And all decay, all radioactive decay is spontaneous. Again, what does it mean to be spontaneous? It will just happen on its own. But some elements decay very quickly. They have very short half-lives. Okay, like this is technetium. Technetium-99 is this decay right here. Very fast. That's opposed to something like uranium-238, which we can't even show how much it starts to decay because its half-life is like 1 billion years. Okay, but does it do it spontaneously? Absolutely. Just because it's spontaneous doesn't mean it has to be fast, and vice versa, right? Diamonds can turn into this other kind of carbon called graphite. That's spontaneous if the conditions are right. Okay, you got to have the right conditions. Usually it means very, very high heat. Okay, 1,000 to 2,000 Kelvin. But that's a spontaneous process. So where would this be happening? Down in like the, what is it? What do we have? Mantle? Wait a minute. What are the parts of the Earth? I know there's the core. And then the mantle and then crust. Is that it? Is that the only parts we have? I don't remember. It's been a long time since Earth science, y'all. Anyways, this can happen spontaneously deep down in the Earth is what I'm trying to get to, right? Okay. Just because something is exothermic does not necessarily mean it's spontaneous. You might think, well, endothermic requires us to put energy in, right? So therefore, that can't be spontaneous. Doesn't that require us to put it? Doesn't necessarily mean I have to put in energy. Something else could naturally be putting energy into it, right? The spontaneity is about us, the observer, not doing anything, okay? So just because a reaction is endo or exothermic, that does not predict if it's spontaneous, okay? Outer core, inner core, and then mantle, and then crust. I know what I'm talking about in my head. I know what order it goes in. Now, just as an example of this, right? It depends on the conditions, okay? We know that when water does what? What is this process called? Solid to liquid. That's called a what kind of process? What's the name of that phase change? Woo, we need to go back to chapter 10, y'all. Is this a fancy one? I don't know. Y'all tell me. This is melting. We talk about the enthalpy of fusion for melting. Yes, okay. This is melting. Melting is normally a what kind of thermo process, endo or exo? Do you have to add heat to make something melt? For sure. That's why this delta H value is what? Positive. Freezing, the reverse process, liquid to solid. That's a what kind of thermo? Exo. So positive and a negative delta H value. But which one of these processes, freezing or melting, is spontaneous at room temperature? Melting is spontaneous for water at room temperature. If I have a piece of ice sitting right here, will it not just melt? That's spontaneous. If I have a piece of ice, excuse me, if I have some liquid water and I have it sitting here at room temperature, will it spontaneously freeze? No. It's condition dependent. So you can't use endo-exo to predict. You got to read the problems and use some common sense, okay? Like, this will freeze right now in my hand. No, guys, come on, let's go. Okay. All right. Look at number 1 on our brand new in class. Just told you guys the answer to this, number 1. True or false? All exo reactions are spontaneous. And that is false. Look at number 2. Can you guys, just using common sense knowledge, tell me if these processes are spontaneous? If I open an oven that's on, if I open that door, the heat will come out of the oven into the room. Spontaneous? Yes. What do we know about how heat moves? Heat always transfers between system and surroundings, right? Heat moves from the higher temperature object to the lower temperature object. That is the way heat moves. Is that a spontaneous process? Absolutely. Okay. Puddle evaporating in the sun, is that spontaneous? Will a puddle not spontaneously evaporate if it's left out long enough? Yes. That's spontaneous. On the sun, I've never tried that. I have not ever tried to. I'll try to cook one on my car hood. Ooh, cookies. What about rusting? Will a car or a bike or a chain that sits out, will it rust spontaneously? Absolutely. Rusting is a spontaneous. Okay. What about water? Will liquid water turn into ice if it's in a freezer? Is that spontaneous? In a freezer, if you put water into a freezer, doesn't it spontaneously freeze? Yes. Yes. Because it's condition dependent on the temperature of that freezer, right? So what's really the answer here? All of these are spontaneous under the given conditions, right? Okay. So talking about being spontaneous, what is it that actually causes something to be spontaneous? Is there a cause, or is it just there is actually a cause? Okay, that's what we're going to learn about in the next section, but I'm going to describe a little bit here. It's not just energy. Yeah, that's fair to say. It's not just about energy, because if it was just about energy, then endo-exo should predict spontaneity, shouldn't it? That's not what we see. It is also not just about matter. Let me show you all this. So what I have up here on the thing is, so let's say I have a bulb, okay, and a bulb on this side, and in between I've got a valve that I can open and close. Okay. And so I start off when this is closed, right? And I've got some gas particles. Okay. But then what if I open the valve? What is spontaneously going to happen? The gas will uniformly spread out, won't it? Matter wants to evenly spread out. Energy wants to evenly spread out. Is it natural for this valve to be open, yet all the gas stay on that side? No. No, not at all. Is it natural to open an oven door, yet no heat come out of the oven? No, that's not natural. That's witchcraft, right? Let's go away. So both of these things want to spontaneously disperse. Okay, that in fact is how I would actually define spontaneity now. Rather than just saying a process that happens naturally, let's say this instead. Right? What does it mean? Spontaneity means a uniform dispersal of matter. Okay. I said we were going to abbreviate, and we are. Spontaneity means a uniform dispersal. Everybody okay with what is spontaneous? What does it mean to be spontaneous? Okay. Certain things, it's easy to understand that it's spontaneous, like this, like talking about iron rusting. Other chemical reactions, we might not have enough background knowledge to predict. So we're going to learn some tips, some things on ways to predict. And we're going to learn some ways to actually calculate spontaneity as well. Okay, that's what we're going to do in this chapter. So that's the end of section 1. So now we got to talk about how we measure spontaneity. How are we going to talk about spontaneity? First thing we have to learn is a brand new property. A brand new thermodynamic property called entropy. Entropy this thing called entropy can tell us if a reaction is spontaneous or not. Okay. It is not the only thing that can tell us if it's spontaneous, but it's going to be part of the picture. It's going to be part of what we learn about. So what is entropy? Entropy is a entropy is symbolized by the capital letter S. I don't know why. Makes no sense, but that's what it is. Okay. Entropy is us measuring how many ways matter and energy can be dispersed. It's a measure of how many ways. What is spontaneity? Just the fact that it spreads. Entropy is how we measure how much that spread is. Okay, you see the distinction maybe? So sometimes you may hear phrases said like entropy is chaos. Chaos is entropy. The more disorder there is, the higher the entropy. Well, what we're talking about is would you agree that this looks more orderly than this? Everything is collected nice and neat on one side, right? That's more ordered. This is all spread out. Which side has the higher entropy value then? Make a guess. The side where it's more spread out. So we're going to measure how spread out things get. And typically what we'll see is that larger entropy leads to being spontaneous. Okay. Again, spontaneity is condition dependent, right? Okay. I can't look at just entropy to tell. I got to look at a lot of things, but it tends to favor spontaneity. The bigger the S, the more spontaneous something is. So sometimes we say entropy is when it just gets more chaotic. It just gets more and more spread out. That's what we say sometimes. Let me tell you the units of S that we'll see, and then I'm going to draw a little something for you. S is going to typically be joules per Kelvin. We may see when we start looking at more chemical reactions directly, we may also see joules per mole Kelvin. Okay. But joules. Entropies are small values compared to things like enthalpies. Enthalpy values are measured with the unit kilojoules typically. These are measured with joules. Okay. This is a thought. What if you had, okay, kind of like I do the thing, what if I have two boxes? Yes? I got two boxes. Like I had two bulbs. What if I have these two particles? Let's say I got a red particle and I got a blue particle. These two particles can go in either box. How many other ways can you come up with to draw this system? You have to have two boxes. You have to have a blue particle and a red particle. That's your conditions. How many other ways can you come up with to spread out these particles? What's something else we could do? Put both of them on the left side. Okay. This is different from this. Okay. Left side, right side, different. Okay. What else could you do? Blue on the left and red on the right? Sure. And then other way? No. Okay. How many different ways did you just come up with to disperse this matter total? How many different ways are there? There's 4 ways total. Guys, this is what we do in chemistry is think about how many particles we have and how many different ways they can occupy different configurations. Okay. This is something called microstates. We're not actually going to do any more with microstates. We're not going to calculate microstates. We're not going to do anything. I just wanted to show you this thought process because, guys, this is what chemists do. We think about all the ways stuff can be arranged. Is it hard? Yeah, it's hard. It's very hard. It's very time consuming. We got computer programs that do it for us now. Okay. But this is how we measure entropy. How many ways can you spread out the matter? The more ways it can spread out, the larger your S value is. But sometimes we don't want to do this calculation. We just want to make a prediction. So that's what we're going to look at when we come back from break. Is how can I just make a prediction about the entropy value, okay, rather than doing a calculation. So we're going to do, oh yeah, we might talk. I think this is what we'll pick up. Okay, go ahead and take a break.